Good morning, my students. I'm going to start today determinants. So already matrix is completed. So matrix is just an arrangement. It has no value. Okay. Whereas determinant is a value. It has a value. Okay. So first I'm discussing what is determinant. Okay. So consider the system of linear equations a1x plus b1y is equal to c1 and a2x plus b2y is equal to c2. And we can represent these linear equations in the form of matrix. So matrix equation is corresponding matrix equation is, so this is the corresponding matrix equation, and here this is the coefficient matrix, here is the variable matrix, here it is the constant matrix. And on solving these two linear equations we'll get x and y values. These are the x and y values. Okay, and here you have both in x and y. What is the denominator? a1 b2 minus a2 b1, a1 b2 minus a2 b1. So if this number not equal to 0, then only x and y are exist, and hence we say that given system has unique solution. The given system has unique solution. So that means the number a1 b2 minus a2 b1. So this is also, we represent this in this form. So this is just a notation, just notation. So instead of remembering these big expressions, okay, because we can't remember these x and y values. So b2 c1 minus b1 c2 by a1 b2 minus a2 b1 means remembering this one is difficult. And I'm denoting this a1 b2 minus a2 b1 by this. So this is called 2 by 2 determinant. So determinant of a1 b1 a2 b2. Okay. Suppose if this number not equal to 0, if that number not equal to 0, so then only this given system of equations has unique solution. That means that this number determines uniqueness of the solution. This number determines the uniqueness of the solution associated to the square matrix capital A is equal to a1 b1 a2 b2, the square matrix capital A, which is whose order is 2 by 2. Okay, so and this number is called determinant of A, and this number is called determinant of A. So determinant of A is denoted by the symbol det, det of A, or this symbol. So don't read this as a modulus of A, it is a det of A. So det of A is a number. Suppose what if A is a square matrix of order 1 by 1, so it has only one element. The element itself is a determinant of that square matrix. So thus determinant of a1 b1 a2 b2 is equal to what? a1 b2 minus a2 b1, just cross multiplication. So a1 into b2 minus a2 into b1. Okay, and you know how to expand 3 by 3 determinant. So that means a determinant of order 3 by 3. Okay, so next I'm going to discuss minor and cofactor. So consider the determinant. So I'm taking some example to understand easily. 1, 2, 3, 4, 6, 7, minus 2, 3, 4. So here what is the element A31? So it is minus 2. And minor of A31 is denoted by M31. And minor of the element is also some number. Okay, how we can find that minor means, so where this element minus 2 is present in third row and first column, so you delete third row and first column and you will get 2 by 2 matrix. For the 2 by 2 matrix determinant, the determinant of the remaining 2 by 2 matrix is the minor of the element A31. So it is the minor of A31. Okay, so remove third row and or delete third row and first column, then you get 2 by 2 matrix. The determinant of this 2 by 2 matrix is the minor. So 2, 3, 6, 7. So what you will get? 14 minus 18. What do you get? Minus 4. And how cofactor? What is a cofactor? So cofactor of A31, small a31 is denoted by capital A31. And how we can obtain? So cofactor of Aij is equal to minus 1 power I plus j into minor of the element. So cofactor of A31 is equal to minus 1 whole power row index 3 column index 1 into minor of the element M31. So minus 1 whole power 4 into M31. What is M31 value? Minus 4. So minus 1 whole power 4 is 1. 1 into minus 4 is minus 4. So thus we can, so in the same way we can find minor and cofactor of remaining elements. Okay. Suppose next I am going to discuss cofactor matrix and adjoint matrix. So what is the cofactor matrix of a given square matrix capital A? So how we can find cofactor matrix of the given matrix capital A? Okay. So the cofactor matrix of square matrix capital A can be obtained by replacing the elements of capital A by their respective cofactors. And transpose of cofactor matrix is what? Adjoint of A. Transpose of cofactor matrix is what? Adjoint of the square matrix capital A. Okay. And remember, we can find only determinant for square matrices. Okay. So in this topic, matrix means you have to understand square matrix. So determinant of the matrix means determinant of the square matrix only. Okay. Next, I am going to discuss some properties, some important properties. So which we will learn already in theory also. Just I am going to recall. So the first property is, I am not going to write, just I am discussing. The value of the determinant is unchanged if the rows and columns are interchanged. If the rows and columns are interchanged, the value of the determinant is not changed. That means from this property, what we can say, determinant of the given matrix is same as determinant of its transpose. Determinant of A transpose. So for this, I am taking some example. So I am taking delta 1 is determinant of 1, 2, 3, 4. I am taking delta 2 is delta 2 obtained from delta 1 by interchanging the rows and columns. Then what you will get? First row 1, 3, second row 2, 4. Now if you expand in both cases, what you will get? 4 minus 6 minus 2. And here also what you will get? Same, minus 2. That means what we can say that delta 1 is equal to delta 2. This is the first property. If we interchange the rows and columns, the value of the determinant is not changed. Okay. Next, second property. If any two rows or any two columns of a determinant are interchanged, then the sign of the determinant changes. If any two rows or any two columns are interchanged, so then the sign of the determinant changes. That means plus become minus, minus become plus. So same example only, you take delta 1 is same example, and I am taking delta 3 as, by just I am interchanging the column 1 and column 2, or you can interchange the first row and second row. If I interchange the column 1 and column 2, what I will get? 2, 4, 1, 3. So here, what you got? Delta 1 value? Minus 2. Now delta 3 is obtained from delta 1 by interchanging column 1 and column 2. Now you need to get, answer will be plus 2. Because here you got minus 2. Sign changes means plus 2. You need to get plus 2. Check. 2 3s are 6. 1 into 4, 4. So 6 minus 4, 2. So thus what we have, delta 1 is equal to minus delta 3. Suppose you take delta 4, interchange the first row and second row, then even in that case also you will get, so delta 1 is minus delta 4, sign will be changed. Next, third one, if any two rows or any two columns of a determinant are identical, then the value of the determinant is 0. Okay, if any two rows or any two columns are identical, the value of the determinant will be 0. So for example, determinant of 1, 2, 3, 4, 5, 6, 1, 2, 3. So what is the value of this determinant? 0, because first row and third row are identical. Hence the value of the determinant is 0. And moreover, so here first row, third row corresponding elements are identical. Even they are proportional with same proportionality. With same proportional, if they are corresponding elements are same proportional, even in that case also value of the determinant is 0. Suppose here 1, 2, 3 you have. So you take you multiply first row with 5. What you will get? 5, 10, 15. So suppose if it is 5, 10, 15 is the third column elements, even in this case also the value of the determinant is 0. Okay, that means if any two rows or any two columns are identical or proportional, okay, then in both cases the value of the determinant will be what? 0. Okay, next this is the third property. Next one more, fourth property, if each element of a row or a column is equal to 0, then the value of the determinant is 0. Okay, next property. Next property, if each element of a row is multiplied by a constant k, then its value is also multiplied by k. If each element of a row or column is multiplied by some constant, say k, then the value of the determinant is also multiplied by k. So for example, if I take delta 1 is equal to ka, or else directly I take the meaning of this property is, suppose first row is ka, kb, kc, and next is d, e, f, g, h, i. So it is equal to k times of a, b, c, d, e, f, g, h, i. That means if any elements of any row is multiples of k, then we can take k common. We can take k common. Okay. Suppose if the elements of any column are multiples of k, we can take k as common. But in case of matrix, if all the elements of the matrix are multiples of k, then only we can take k common. But in case of determinant, we can take that k common either row wise or column wise, only single column or single row. If you see each element of a single row is a multiple of k, then you can take k common. If each element of a column is a multiple of k, then we can take k as a common. Next property. If some or all elements of a row or column of a determinant are expressed as a sum of two or more terms, then the determinant can be expressed as a sum of two or more determinants. So the meaning of this property is, so if some or all elements of a row or column of a determinant are expressed as a sum of two or more terms, then the determinant can be expressed as a sum of two or more determinants. That is, determinant of, suppose a plus k, b plus k, c, d. So here all the elements of first row are what? Sum of two terms. Then this can be expressed as a sum of two determinants in the same order. That is det of a, b, c, d plus det of k, k, c, d. So if you got it out, expand on both sides, you will get LHS is same as RHS. Next, if each element of a row or column is equal to 0, then the value of the determinant is 0, already discussed. Next property, the value of the determinant unchanged if we apply the row operation like Ri goes to Ri plus k into Rj. Like R1 goes to R1 plus 2R2, R1 goes to R1 minus 3R2, etc. If we apply these row operations in the same way, so those kind of column operations, so like column operations, Ci goes to Ci plus k into Cj, like C1 goes to C1 plus 2 C2, C1 goes to C1 plus 3 C3, etc. If you apply either row operations or column operations, then the value of the determinant is not changed. Okay. For example, delta 1, if I take 1, 2, 3, 4. So already we found this value, what we got, minus 2. And delta 2 is obtained by applying the operation R1 goes to R1 plus R2. So what you will get, R1 plus R2 means 4, it is 6, 3, 4. Then expand, what you get, 16 minus 18, what you got, minus 2, same only now. Okay. Next to, this is the important property. So if we put x is equal to a, then the value of the determinant vanishes in the sense 0. Then x minus a is a factor of that determinant. By putting x is equal to a, if the value of the determinant is equal to 0, then for that determinant one of the factor will be x minus a. Suppose if suppose if we go in some more depth, suppose by putting x is equal to a, if 3 rows are identical or 3 columns are identical, then x minus a whole square x minus a whole square is a factor. Okay. If by putting x is equal to a, 4 rows are identical, then obviously x minus a whole cube is factor. By putting x is equal to a, if n rows are identical or n columns are identical, then x minus a whole power n minus 1 is a factor. Okay. Next to last property, it is the important property. So in your determinant, sum of the products of the elements of any row or column with their corresponding cofactors is equal to the value of the determinant. In a determinant, sum of the product of the elements of any row or column with their corresponding cofactors is equal to its determinant. For example, A11, that means I am considering first row elements. What are the first row elements? A11, A12, A13. So the sum of the products of the corresponding cofactors of any row or any column with their corresponding cofactors is equal to its determinant. So A11 and cofactors are capital A11, capital A12, capital A13. Sum of the products. So this is equal to what? Det A. Similarly, A21 into capital A21 plus A22 into capital A22 plus A23 into capital A23, it is also what? Determinant of A. Suppose A11 into capital A11 plus A12 into capital A12 plus A13 into capital A13, it is also what? Value of the determinant. But if we consider the sum of the products of the elements of any row or column with their corresponding cofactors of any other row or column, then its value becomes 0. Its value becomes what? 0. That means I have taken first row elements and second row cofactors, and I am multiplying corresponding elements and adding. Then what I will get? Sum will be 0. So that means A11 first row element, capital A21 second row cofactor. Okay. A12 into capital A22 plus A13 into capital A23. So its value become what? 0. So I have taken elements of first row and cofactors are second row. So 0. So using these two properties, we can prove that A into adjoint A, capital A into adjoint of matrix A is equal to determinant of A into identity matrix, which is same as adjoint of A into A. A into adjoint A is equal to det A into I, which is same as adjoint A into I. Thank you. In the next session, I will discuss some important formulas. Thank you.